Saturday and people are not coming as big numbers as before. But nevertheless, I want to give one last lecture. And let me recapitulate what we proved since the beginning of this course. So we proved a certain number of things in deterministic setup. So if you have a curve, then you have a driving function beta t, and you have a family of conformal maps gt. And I'm not specifying if it's radial or chordal, but because that's, at this level it's not relevant. And what we had was the theorem by Schramm saying that if you have a discrete model, and in the limit you have conformal invariance and a discrete Markov property as delta, as the mesh goes to 0, then you have SLE, in the sense that the limiting curve can be described by a Loeffner chain, and the driving function will be square root of kappa times bt. So beta t is square root of kappa times bt. Okay, so this was very smooth. This was, in fact, not very difficult once you have all the tools. And then there was a list of results saying that if you have a locality, then kappa is equal to 6. If you have a restriction, then kappa is 8/3. If you have Cardis formula, and then kappa is equal to 6 as well. But the assumption was always that there is a scaling limit. So for all these, we are assuming that the discrete model has a limit as the mesh goes to 0. We are assuming that it fits in the framework of SLE, and we wanted to catch the value of kappa using this assumption. What I haven't told you yet, really, is how to actually prove that there is a scaling limit and how to prove that this scaling limit is given by one of these curves. So there's one thing I almost wrote. If you combine what I told you about the Brownian motion and what I told you about percolation, you can come out with one particular statement of the existence of a scaling limit, and that's for percolation. So what I told you was if you look at percolation in a domain with 4 boundary points, then the probability that there is a crossing converges to something given by Cardis formula. What you can extract from the proof is this. If you take the exploration of percolation from A to B, and say that you look at it until the first time it hits somewhere here, then you get some shape like this. You get a curve at the discrete level, and the curve touches here. And then if you fill it seen from the outside, so you fill the holes of the curve, you get some kind of compact set like this. If this is what you are interested in, then we have all the ingredients we want, because the shape of this guy is characterized by the probability that you don't intersect obstacles touching the boundary. And if you want the probability that this does not intersect the hull A, well, this is exactly the same as saying that the exploration touches the boundary here without touching this. And that, again, is a crossing probability in a domain which is omega minus A. And this we know how to compute. So the outer shape converges by Cardis formula. So that's about the Cardis-Smirnov formula. So this is very nice, and you can rebuild the whole proof by putting this remark with the actual reasoning I used for proving the conformal invariance of Brownian motion. So this is very nice, but it doesn't tell us anything about the curve here. So the curve is completely drawn by the filling procedure. And if you want to say something about the curve, if you want to know that the actual exploration process converges to SLE6, then we'll need a new argument. So this is what I want to tell you during this last lecture. It will be something about convergence to SLE. So I'm not going to give a very general proof. I will give you the proof in one particular case, but everything I tell you will apply to most of the cases for which we know what to do. And the framework of the proof will be essentially the same in all cases. So what I want to do is to prove that the UST exploration converges to SLE8. So this is a theorem, and I have to tell you again what the UST is, what the exploration is. I don't think I told you this already. And then I will tell you how to prove that this curve actually converges to an SLE for kappa equal to 8. So if you remember what I told you in the first lecture, I told you about the loop erase random walk. So you just take a domain, you launch a simple random walk from some point inside the domain, and you erase the loops as they are created, and you continue until you touch the boundary, and it gives you a curve from 0 to the boundary. So if you want to prove that this has a scaling limit, you just take this proof here, and you can extract the main argument, and then you will see what you have to replace if you want to prove convergence of this guy as opposed to convergence of this guy. So nevertheless, we have an object that is the loop erase random walk, and I told you just at the end of the lecture that something very related to that was the uniform spanning tree. So if you have a graph, you can look at all the subgraphs that have no loops and which contain all the vertices and which are connected. So there are trees that are spanning the graph. And if you take a uniform measure on spanning trees, you get what is called the UST, the uniform spanning tree. And the main link between the two was that the branch between A and B in the uniform spanning tree is a loop erase random walk from A to the first time it touches B. So there is a link between the two. And the good thing about this is that we can look at the uniform spanning tree, which is something which is a priori complicated, but use arguments from simple random walks, and loop erase random walks are essentially simple random walks, to derive information about the UST. So if we want to show that there is convergence to an SLE, it would be a good thing to have a curve. So here is the picture we'll look at for this whole lecture here. So I want to start with the domain. So the domain will be omega. And I will fix two boundary points. And again, I'm looking at the scaling limit. So you should think of this domain as discretized. So there will be a parameter delta. Delta will be the mesh of a lattice that discretizes omega. So let's say it's delta times z2, just to fix the ideas. Okay, and we have these 2 points on the boundary. And we want to define a spanning tree in such a way that there is a natural curve associated to it. So as it turns out, one thing you can do is to look at boundary conditions that are essentially the same as what we use for percolation. So Dobrushin boundary conditions, we consider this part of the boundary to be wired, which means that this is just one huge vertex of the graph. And this part of the boundary is free. There is no connection in addition to what is really inside omega. So you just wire one half of the boundary to get something a little bit more asymmetric somehow. So this is the starting point. It will be called A. And this is the endpoint, B. And now we want to look at a spanning tree inside this domain, but with just one vertex here. So the spanning tree is just something that will be attached to this part of the boundary. And the idea you should have in mind is that it would look like something like this, like plenty of trees that are growing on this part of the boundary. So maybe something like this. Maybe. So this is a typical spanning tree of this domain. And it touches the boundary many times here. So what can we say about the scaling limit of this guy? Well, essentially for now all we have is convergence of, well, is the link between this and the loop erase random walk. So what it tells us is that if you have a point here, then the branch, maybe I'll use some color here, the branch between this point on the boundary, so this curve here, this is exactly a loop erase random walk started here until the first time you touch the wired part of the boundary. So if you want, it's reflected on this part of the boundary and it is stopped when it touches the wired part of the boundary. So this curve here is just loop erase random walk. So of course it doesn't help because we don't know that loop erase random walk has a scaling limit. But you can go the other way, and once we know that the UST has a scaling limit, we can probably extract that the loop erase random walk as well has a scaling limit. So this is not the way to catch the scaling of this curve. So as I told you, we need a curve. And as it turns out, there is one very nice way to build a curve out of this. It's using duality. So I told you about duality already in the case of percolation, and you heard lots of things about duality in the course on sensitivity. So here's one thing you can do. You can look at the dual lattice. So if you start with the initial lattice like this, the dual lattice is just a translate of Z2 by 1/2 in each direction. So there will be a dual graph, a dual lattice somewhere here. And then you can use the same duality as the usual one for percolation. You can decide that a dual bond is open if and only if the corresponding primal bond is closed. And what you get is this, that there will be some boundary here. And you should think of it as shifted a little bit by 1/2. And then the dual of this tree will just be, again, a tree. But this one will grow here on this part of the boundary. So it's like self-duality. Really, you will have two trees, one growing inside the other one, like this. And maybe if I finish the picture, something like this. So you will have two trees, one inside each other, the other one. And the yellow one is the dual tree. And what you can do if you have two trees like this is the same as what we did for percolation. You can just explore the common boundary between the two. So here I will not do the whole picture, but you just start at A, and you just go between the two trees, like this. And you start going, and you cannot stop anywhere, except when you arrive at the other side of the lattice. So eventually you will come out at B. So this is what I want to call gamma delta. So this is the exploration of the spanning tree. And if you start with the uniform measure on spanning trees, then what you get for gamma is the uniform measure on space-filling curves inside omega. So gamma delta is called the uniform Peano curves. So it's uniform out of all the curves that you can obtain as an exploration. So of course you need to be a little bit careful if you want to define it in a discrete way. Here is what the picture can look like. So this is the tree. Maybe it goes like this. There is the dual graph. The dual graph has bonds like this. And then formally, if you want to define the thing properly, you need to say that the path gamma lives in the medial lattice, and it will just wind around like this. So you can just continue like this, and you get a path in the medial graph. And you can check that it contains all the bonds of the medial graph. So this is the object we want to start with. This is a curve. So the natural conjecture is that this curve would have a scaling limit. And the theorem will be that this gamma delta will converge to the trace of SLE8. So this is a more explicit version of the theorem. We know now what gamma delta is. We let delta go to 0, and this converges in distribution as the mesh goes to 0. So the question is, how do we prove such a convergence? And as it turns out, it goes in a few steps, but mostly there are two steps that are essential. Did I forget anything? No. So there are two steps. First of all, you need to identify the limit, and second, you need to prove that you actually converge to the limit you identified. And I will just start with step 2, because, well, I'll rename it step 1, but that's the second I mentioned. So step 1 is something to do with tightness. So that's always the same argument. It's something that you learned in much detail in the course on planar maps. You have a discrete model, and you want to show that there is a limit. So the first thing you can do is to use some kind of compactness argument to show that there are subsequential limits. And then you will have proved convergence if you can show that the subsequential limit is unique and well-defined. So here, what you have is a curve in the domain. And you want to show that there is some compactness. You want to show something that looks like the Ascoli theorem. You would like to show that these curves are equicontinuous. And the problem is that they are not parameterized by time, so you would need some version, some geometric version of the Ascoli theorem. Essentially, what you need is something like that. You need the existence of some function f from 0 infinity to 0 infinity, such that if you take any 2 points x and y inside the domain, and if you look, so if you take these 2 points, of course these 2 points, they are on the curve because the curve goes everywhere, so there is a sub-curve between them. So there will be a loop like that. The curve starts somewhere at A, and it passes through one of them and then the other one. And what you want to know is something about the diameter of this set. And if this diameter is controlled as a function of f uniformly in delta, so if the diameter of omega from x to y, this will mean just a part of the curve that goes from x to y, or from y to x if it's the other ordering. If you can show that this is smaller than the constant times f of the distance y minus x with high probability uniformly in delta, something like that. So this probability is large uniformly in delta, then this will be your tightness results. You want to say that what you want to rule out is the fact that you don't look like a continuous curve, because if you don't, if this fails, of course f is continuous and f goes to 0 as 0. Of course, if you don't have this, then the limit can be almost anything. It has some topology, but it will just blow out at every scale. So there is no hope that there is a scaling limit. But if you have this, it tells you that all these curves are continuous enough that you can extract the converging subsequence. So I don't have much time to tell you exactly how to prove this, but here is one thing you can look at. How would you prove such a thing for the loop erase random walk? A priori, it's easier to do it for the loop erase random walk because it's a simpler curve. It wants to be smooth already. And then once you have it for the loop erase random walk, you can look at the branch inside the tree. And once you have the branch inside the tree, well, the exploration curve essentially follows the branch in the tree and has to use the subtrees. So there are still lots of technicalities to add. But let's look at what happens in the case of the loop erase random walk first. So we have 2 points, x and y, and we want to show that if you take a loop erase random walk and the loop erase random walk uses these 2 points, then the loop from x to y is not too big. So here is the picture. This is x, this is y. And we want to control something about the loop erase random walk from x to y. We want to know with probability this excursion here somehow is bigger than a large number of times this distance here. So I told you that there is a link between the loop erase random walk and the uniform spanning tree. There is something I didn't remind you of yet, but I mentioned it last time. It was Wilson's algorithm. So remember, the way you can build the uniform spanning tree is you start with the empty configuration, except of course it's wired here. You pick a point at random and you make a loop erase random walk to the boundary. Then you pick another point and you make a loop erase random walk to the boundary. And then you pick a point and you take a loop erase random walk to the boundary of the current set each time. So maybe you attach to something you already have. Maybe you attach to the boundary. And you can just continue like this until the whole domain is filled. And what you get is the uniform spanning tree. So that's a very nice algorithm. What it tells you really is that the distribution of what you get does not depend on the order in which you choose the points. So one very nice trick that is also in the article by Schran, to control the loop erase random walk from x to y, what you can do is to cheat somehow to pass through the uniform spanning tree. So what you can do is pick some point z, which is far away, and say, okay, maybe instead of looking at the loop erase random walk from x to y, I first look at the loop erase random walk from x to z. And it's very likely that this does not contain y, because it's very likely that the simple random walk will go here without touching y. So this is the loop erase random walk from x to z. If you do touch y, then maybe you start at y instead. You can just see what happens in that case. But assuming that you don't touch y, then what you can do is then you look at the loop erase random walk from y to the boundary of the current set, and maybe you touch here at point w. And once you have done this, well, this part of the curve here, this is exactly the same as the loop erase random walk from x to y. This is by the abelian property of Wilson's algorithm. So what it tells you is that if you want to control the size of the loop from x to y, it's enough to show that if you start a loop erase random walk from y, it will touch this white curve very close to x. Once you have this, then you get to control on the length between x and w. And by symmetry, well, this is an estimate on the size of the loop from x to y. And now if you have a loop erase random walk from y to something with a large boundary like this, well, you know that you touch the boundary whenever the underlying simple random walk touches the boundary. And a simple random walk is very likely to touch the boundary close to its starting point, because it's difficult for a simple random walk to get away from the boundary without touching it. If you want uniform estimates, they are known as Berling bounds. You can see that using scaling. I mean, the probability that you end up at a distance which is more than your starting point, your starting distance times 2 to the n, this decays exponentially in n. So in particular, the probability that you touch away from an initial segment of size x minus y times 10, this is small. And as 10 goes to infinity, it's smaller and smaller, like a power law. So what you get is that typically, the distance between here and here behaves like y minus x to some power epsilon positive. So I'm not putting every detail here because that's just the general idea. What really you should keep out of this is that if you know something about the underlying model which tells you about the regularity of an interface or regularity of a curve, then you can extract something quantitative like this, and it will tell you that you get some tightness in the family of curves that you're looking at. And in the case of the previous random walk, it's not very difficult to obtain a bound like this. Okay, so what it means is that as delta goes to 0, you can extract delta k going to 0 such that gamma at scale delta k converges as k goes to infinity in distribution to a continuous curve. So gamma a continuous curve. In the case of the loop-based random walk, you can even ensure that the limit is supported on simple curve by saying that almost closing a loop is difficult, and you can roll it out in the limit. Of course, in the case of the uniform spanning tree and the piano curve, you do expect many loops like this. So there is no hope that gamma would be a simple curve, but nevertheless, it is a curve. It has the right topology for SLE, in the sense that it cannot cross its own path because the discrete one cannot. So you are very happy. You have a continuous curve in omega from A to B. So the second step is to identify gamma as SLE8. And that means, in particular, proving that there is conformal invariance in the model and that there is the domain Markov property. Once you have this, you have an SLE, and then what you need to do is to identify the value of kappa, but this will actually come out of the proof directly, so it will not be a separate step. So what about the domain Markov property? Well, in the case of the uniform Peano curve, that's very easy to do. Look at what happens when you have explored a certain number of steps on the interface. So this is your domain, this is A, this is B. And you start exploring from A for some time and say that you arrive here. So what does it tell you? It tells you that along the left part of the exploration you have open bonds, and along the right part, the right side of the curve, you have dual open bonds. So just to use the same colors here, you have dual open bonds here. You have open bonds that are supposed to be red here. And there is the boundary condition that was red here and yellow here. And that's it. What we have to start with is a uniform Peano curve in a domain. If you condition it by the first initial segment, what you get is the uniform measure in the possible continuations of this. And the possible continuations are exactly Peano curves in whatever remains here, which is a domain with double routine boundary conditions, yellow and red here. So this is exactly the domain Markov property. You condition by the beginning, and you get the process in the complement of the beginning. So that's okay. It comes for free. And that's a typical case. The domain Markov property, if you start with a discrete model, and if you want to prove it at the discrete level, it's never really difficult. It comes out of the definition of the model. So we need something now about conformal invariance. And this is what will take the rest of the lecture today. So how about proving conformal invariance of the exploration curve? Well, the first time you see the question, you really don't know what to do, because proving that something is conformally invariant, this typically requires some thinking. And here it will be essentially a byproduct of something else. So the main idea is that we will introduce some observable, and I will tell you what this is. Something that we can, so just to keep in mind, what we want is something that we can compute for fixed delta, or that we can estimate for fixed delta, that has a limit as delta goes to 0, and for which the limit is nicely behaved. So think as something like this. For percolation, we had 3 points here, a point here, and we had the probability that there was a simple curve separating a point inside the domain from a part of the boundary. This is the kind of thing that you should have in mind as observable. It's just something that depends on the geometry of the system, and that you can prove that it converges to something in a scaling limit. So as it turns out, there is one very nice observable here in the case of the UST, which goes like this. So you have a domain where you have 2 points on the boundary. I will introduce a third point on the boundary, C, between A and B. And I will introduce a point inside the domain, somewhere. So that's Z. And the observable will be telling you something about the geometry of the tree as it relates to the location of A, B, C, and Z. And to get it in the right direction, okay. Yes, it's in this direction, yes. So here you have, of course I got it wrong with my notation. So in your mind you should switch the yellow and the pink here, so wired is here and B is on the wired component. So this is wired, really. Of course, that's not very different, but so you have this uniform spanning tree that starts on this part of the boundary, and it contains bushes. And the thing you might want to know is how Z is connected to the boundary. So there are 2 parts of the boundary. There is the boundary 1 here between A and C, and boundary 2 between C and B. And the event that we want to look at is E, which depends on Z and B and C. A and B are supposed to be fixed. So this depends only on Z and C. Is the event that there is a path which I don't want to name. So in the tree, in the uniform spanning tree, connecting Z to the boundary number 2 without going through boundary 1. So what it really means is that if you follow the branch of the tree from Z to the boundary, you know that you will touch between A and B because that's how the boundary is defined. But really, you will land somewhere between C and B here. So you don't reach this part of the boundary, you reach this part of the boundary. Okay, so this is an observable. If you can compute this, then it tells you something about the shape of the tree. It tells you that if you explore the tree from A using this procedure here, by the time you reach Z, you have essentially swallowed everything up to C. Because if you don't, when you hit here, the right boundary of your exploration is a path that connects Z to the boundary delta 1. So essentially, it tells you something about the order in which you visit C and Z in the exploration process. And this is something that makes sense in the limit, that the scaling limit will visit C before it visits Z. So that's good information, and it will make sense in the scaling limit. Well, the thing is, we won't use this information in the scaling limit, but this is what the observable tells you. So what is the probability that this occurs? How can you compute such a probability? Well, there is one very nice way to do it. It's to use Wilson's algorithm. You can assume that the tree was produced by Wilson's algorithm. And in addition, you know that everything is independent if you start from different points in different order. So what you do is you do Wilson, but the first point is Z. So the first step of the algorithm will be you start with Z and you take a loop erase random walk in the domain until it touches this boundary. And then you erase the loops, and it gives you exactly this branch here. So what you get is the probability of E, Z, and C is the probability that the loop erase random walk from Z lands on boundary number 2. But now that's something I already told you the first day, and it's just the definition of the loop erase random walk. The point where it lands on the boundary is the same as wherever the simple random walk lands on the boundary. So this is the probability that simple random walk lands on boundary number 2. Okay, the simple random walk, let's say by lands, I mean the first time you hit delta 1 union delta 2, this is actually in delta 2. So this simple random walk is reflected on boundary number 3, and boundary number 3 is this. So really what you have is you start from Z, you take a simple random walk, it's allowed to touch this part of the boundary, but you stop it when it touches that part of the boundary, and you have a landing point, and you want to know the probability with which this landing point is to the right of C. Okay, now we have this domain, we have some discretization of the domain. The simple random walk, of course, lives on the discretization. But we know that simple random walk converges in the scaling limits to Brownian motion in this domain. So this will converge as delta goes to 0. And that's something we want. We want something to converge in the scaling limit. This converges to the probability that Brownian motion in omega reflected on boundary number 3 hits boundary number 2 before boundary number 1. So this is perfectly well defined. You have a domain, you have 3 boundary parts. You take Brownian motion, it's reflected on the third one, and you want to know if it hits the second one before the first one. So this is really the picture. So I told you we want an observable, we want it to be converging in the scaling limit, and we want it to be computable. So we would like a formula telling us the probability of this event. And something else we would like is conformally invariant. And we know that Brownian motion here is conformally invariant. So even if we don't manage to prove that this is computable, if we don't manage to compute the limit, in any case, we know that the limit is conformally invariant. Because it's something to do about the heating distribution of Brownian motion on the boundary. So the problem is conformally invariant. Well, as it turns out, we know how to compute the limit, and it's using a conformal map. So this is the domain omega, and I will choose a map phi, mapping omega to the upper half plane, because I like the upper half plane. We have here 3 boundary points, A, C, and B. Well, I will just send here A to phi of A, C to phi of C. This I will call big A. This I will call big C. And B, I will send it to infinity. So somewhere here is phi of B equal to plus infinity. And Z will be sent to big Z here, which is phi of little z. Now we know that Brownian motion is sent to Brownian motion on the right, and reflected Brownian motion on the boundary will be just sent to reflected Brownian motion here on the upper half plane. So what you have here is a Brownian motion from big Z in H. So this is the second part of the boundary, boundary 2. This is the first part of the boundary, and this is the third part of the boundary. And you have a reflected Brownian motion from Z. So this Brownian motion, it's allowed to touch this part of the boundary, and it's reflected on it. And you want to know with which probability it touches to the right of big C. If you can compute this, this is the limit of this probability. So let me just tell you how to do something like this. Well, either you are fluent in all the Dirichlet, Neumann, whatever boundary problems, and then you just know it by heart, or you can say that, okay, the Brownian motion will be reflected on this part of the boundary. Well, you might as well allow it to cross this part of the boundary, and just say that the way you reflect it will be where you take the Brownian motion in the whole domain, but whenever it's below, the reflected one will be above. That's one way to define reflected Brownian motion. It's not general. You cannot do it in all cases like this. In particular, in omega, it would not work because the boundary is not flat. But here, if you want to live in H, then it works perfectly well to do like that. So instead of reflecting Brownian motion, I will just allow it to continue here. And maybe a path will be like this. And now, if you look at what we want the Brownian motion to touch boundary number 2. But now boundary number 2 has 2 sides. It's also possible for the Brownian motion to touch below here. And that's allowed. It will be reflected to the top. So what you want to know is the probability with which you touch one of these 2 sides of the boundary before you hit anything that is blue here. So blue is forbidden, and yellow is allowed as an exit point. So this is still big A, this is still big C. And this goes all the way to infinity. Okay, how do you do that? Well, there's one last thing you can do. You can see that now you live in a plane minus a half line. You want to look at Boolean motion in this domain. And you know a lot about Boolean motion in the half space. So you want to map this to the half space using something like a square root around A. So you will map the picture by square root of Z minus A. What this does is that it takes the slit domain here and it opens the slit and it maps this back to H. So it maps this to H, it maps A to 0, and it maps C. So C is really 2 points. There is C on the top and C on the bottom. And it will map the blue part here to the interval, which is minus square root of C minus A plus square root of C minus A. So this will be the image of the blue part in H. The rest is yellow. Big Z is mapped to square root of big Z minus big A. And then the exit probability is the probability that in the upper half plane you exit outside the blue part. And now you're extremely happy because you know that the exit distribution of Boolean motion in a half plane is exactly a Cauchy distribution on the boundary. So it has density, which is something like dx over x squared plus 1, where the 1 really depends on the distance to the boundary where you started from. And so all you need to do is integrate this between square root of C minus A and minus square root of C minus A. And you get arctangent of something, and you can just compute and finish the computation using simple analysis. Then you need to piece everything together and to write it in terms of the initial domain if you want. But let's say that this tells you how to finish the computation of the heating distribution. And I will write what you get in the end. I will write it as a function of big C and big A and big Z because that's where the formula is nicest. So you know the heating distribution is like a Cauchy distribution, so you will have to integrate dx over 1 plus x squared. And that will give you some arctangent in the limit. And indeed, that's what you get. So the formula you get, I don't know it by heart, but it's something to do with arctangent of Z minus A over C minus A. What you get is this. That's the limits of the crossing probability. So the probability of the event E, Z, and C is some function of Z minus A over C minus A. And this function in polar coordinates is equal to 1 over pi times the arctangent of 1 minus r divided by 2 square root of r sine of theta over 2. Okay, so you find that it's this formula and not something a little bit different. It's not completely essential, of course, but what is essential is that we're able to compute and to get the exact formula. Okay, so you can check the boundary conditions. It should go to 0 if you approach the boundary on the first part, on boundary 1. It should go to 1 on boundary 2. And the cusp between these is given by r going to 1 and theta going to 0. And here you can check that if theta goes to 0 and r goes to 1, well, across 1, this here will be plus or minus infinity. And so this will be 0 or pi, and this will be 0 or 1. So it works, and it has the right boundary condition. So this is just a sanity check somehow that this formula is reasonable. So this was the step number 2, which was the computation of something in the scaling limit, which hopefully characterizes the limit. So I still have 35 minutes plus epsilon to tell you how to go from this to convergence to SLE. And okay, it probably will fit. I will not have time for all the details, but that's probably better because it's Saturday, so we're not supposed to be working on Saturday anyway. So I will be working because I have to write things on the board, but you can relax and just look at the nice pictures. So we want to show that something converges to SLE. And we have a very general theorem telling us that if we have a curve in a domain, we can encode it using Loewen's equation. So one thing you can do, and it turns out to be a good idea if you do that, it's to say that, well, we have a discrete curve, which is the exploration of the discrete spanning tree. But we can always see this curve as a continuous curve, which is just piecewise linear. So it's a broken line, but a broken line is a perfectly nice curve in the plane. So we have this curve, and we can choose to encode it by Loewen's equation. And of course, the driving function will not be Bonnen motion. It will match this fact that the exploration curve is piecewise linear. So it will be something that is piecewise algebraic and which will have discontinuities in its derivative whenever the curve turns. But nevertheless, it says something like this. You will have the domain here. This is A, this is B. And let's look at the first few steps of the exploration. Let's say that this is the first n steps of the exploration. So this is gamma n at scale delta. So this is a curve in the domain. Well, there is a map that maps the complement of this curve to the upper half plane. There is such a map because the complement of this curve is a simply connected domain in the upper half plane. Maybe you have to say that maybe A is not on the boundary because the boundary is the boundary of a continuous domain, and this is really a discrete approximation. So maybe you have to continue it a little bit. Maybe you have to fatten the curve. But it's not a big deal. You can just look at a simple curve and connect it to the boundary artificially, but locally. Then there will be a map that I want to call Gn delta, which maps the domain minus gamma n delta to the upper half plane. It has to be somewhere, so you will want G0 to match the map phi over there. And you want it to look like a Loewen chain. So you want Gn of B to be equal to plus infinity. And there will be this point C here, and there will be a point Z here. And their images will be, so I want to call Zn, which is Gn of Z. This is An, which is the boundary point, so that will be the image of the tip. So maybe I should write something here. So Zn will be Gn delta of Z. An will be Gn delta of gamma n delta. So that's the image of the tip. A big Cn will be the image of little c. So that's Gn delta of little c. And the image of the boundary here is some interval here containing an. So this is an, and this is cn. Okay, and so this is the image of the boundary. So we have a family of conformal maps, Gn delta. And we would like to say something like a Lovener equation. And as I told you, the Lovener's equation is well defined in the upper half plane, but it's not well defined in a general domain. You need to map everything back to the upper half plane. So we need to use the map phi. And what we will write is that Gn, so maybe I will rename this Gn tilde just to match better with what follows. If you want to map the domain like this to H, you might first map the domain to H, the full domain by phi, and then map by something here. So you can always write Gn tilde to be Gn composed with phi. So phi maps the geometry of the initial domain to the upper half plane, but of course it maps the lattice to something deformed here. So it's not saying that we are looking at the model in the upper half plane. It's just some step to write the conformal maps here. And then you have the image of gamma n by phi, which is some curve in the upper half plane, which is composed of pieces of smooth curves with corners whenever this one has a corner. And then you map this back to H by a map Gn here. So now we can fix the normalization. So normalize so that Gn of z is z plus big O of 1 over z. You can always do that. And that's the same normalization as for SLE. And so you can write that Gn of z is z plus Tn over z plus other terms. So Tn is some measure of the size of gamma n of delta. So that's really what you should realize, that Tn is the size of gamma delta between 0 and n. So it's the size in the same way that the capacity was measuring the size of a curve inside the upper half plane. We want you want a way to measure the size of a set in a conformal way. And that turns out to be the right way. So seen from B. Right, so now we have, for all delta, all these depend on delta, of course. For every delta, we get a one parameter family of conformal maps indexed by n. And we get a time parameter t. And what we can do is you can extend Gn delta to Gt delta for t positive, just by saying that instead of looking step by step, you see this as a real curve, and you interpolate along the segments here. So you really get a one parameter family of conformal maps Gt. And for this, you know that you have Lovener's equation. You know that you can parameterize such a curve by a driving function on the boundary and a time parameter on the curve. And the time parameter on the curve is Tn. So maybe there will be some t sub t that will be the time parameter in the continuation here. So this is not the same t. Maybe I should call it tau here. So what you get is something like this, that dt of gt tilde delta of z will be, well, 2 times tau n prime of t, well, it's dt of tau sub t over gt of tilde delta of z minus beta t delta. So maybe don't look at the formula, but all it tells you is that you started with a curve in a domain, a discrete curve. You map it to a discrete curve in H. And it's discrete, but it's what follows is something like looks like this. But it's still, you can still see it as a continuous curve in the upper half plane. You encode it using Loevner's equation. And what you get out of this is this beta t delta, which is the driving process. So this beta delta encodes the whole information about the geometry of gamma n. So this encodes gamma delta. So the natural thing to do if you want to prove that the exploration curve converges to an SLE, one natural step, and it will be enough if you have tightness. So one goal will be now that to prove that as delta goes to 0, this discrete driving process, beta t at scale delta, converges to square root of kappa times bt. So just to say that one last time, you have a discrete curve, you encode it as a Loevner chain, so it has a kind of discrete driving function. And if you want to show that there is a scaling limit, a good idea might be to first prove that the discrete driving function converges to Brownian motion. So of course, because we know that we have convergency distribution here, all we need to know is identify the subsequential limits as SLE kappa. Well, for that, it's enough to show that the limit of the driving function is square root of kappa times bt. So this is what remains to do. We need to show that the driving function converges to square root of kappa times bt, and hopefully what we get is really that it converges to square root of 8 times Brownian motion. And that's what I meant by saying that you get kappa at the same time as you prove convergence. There is really no separate step to show that first it converges to Brownian motion and then you get square root of kappa. There is no real way to prove that it has independent increments. So it will not be a smooth proof. It will be some computation. But as a bonus, it is the computation that you would do anyway if you wanted to compute the value of kappa. So that's okay. I mean, you cannot avoid computations all the time. And this is something you would have to do anyway. So what is the computation you want to do? Well, there is not much choice. We have essentially one tool, which is the observable that we just computed here. There's one thing we know how to compute, so we want to use it as much as possible. What we have now is a domain, and we have explored a little bit. So we have two tools. We have this observable, and we have the domain Markov property. And we want to mix them. So you will recognize something in what I'm going to do. It's something I used when I showed Cardy's formula for SLE. I used the fact that something was a martingale to get a differential equation on the function f that was giving Cardy's formula. And essentially what I'm going to do now is going backwards. So starting from the fact that something is a martingale, and from this derive something about the driving function. So you'll see how it goes. So remember that there is this image of the initial domain by Gn. So we have points An, Cn, and Bn. Now pick little n, so the number of steps in the curve. Assume that n is small. And by small, I mean that you want the initial segment here to still be microscopic. So say you want n times delta to be much smaller than the distance between A and C, and you want the image here to be smooth enough, so you want something like, in terms of the process, you want that a n minus a, so remember a is the image of little a by G0, so this is how the driving function moves. You want this to be smaller than epsilon, and you want Tn to be smaller than epsilon squared. So that tells you that the driving function has not moved too much, and it tells you that the curve has not grown too much. So it's just some small time. The choice of epsilon will not be relevant, but the fact that it's small will come out eventually in the proof. Okay, so now we have this n, we have these first n steps. But because Z and C are far away, this doesn't give you the whole information about whether Z is connected to this part of the boundary. And in fact, well, we don't know yet if it's connected or not. So what we have is that the probability of the event EZC, well, this is the expectation of the probability of EZC given f sub n, which is the sigma field generated by the first n steps of the exploration. So I explore the first n steps, and I see what remains. Okay, we know that this converges to some function which I erased, of course, but it converges to some function. No, it's not erased, it's here. To some function of z minus a over c minus a. F of z minus a over c minus a. And this here, this is the probability that the exploration process inside the complement of the curve up to time n does something in particular. But this, by the Markov property, by the domain Markov property, this is the same as the probability of the same event in the domain which is omega minus the first part of the exploration. So it's the probability that the branch from Z touches between C and B as opposed to between gamma n and C. And what we did to compute the limit of this probability, well, this, given Fn, it converges to f of Zn minus An over Cn minus An. So we want to compute the probability in a domain which is different, which is the domain minus a curve, but it's still given by a conformal map. So we map the complement of this curve to H, and we will something in the limit. But the map from here to H is known, it's Gn tilde. So we can just write the result of step 1 of the observable in this new domain. And what we get is this. So what we have is this, that f of z minus a over c minus a is just the expected value of f of Zn minus a divided by Cn minus An. So this means that f of Zn minus An over Cn minus An, this will behave like a martingale. So I'm cheating a little bit because there will be error terms here. And that's because well, there is a difference between a continuous domain and a discrete model. There will be some estimates to do when you prove that there is convergence here. You need to know how quickly it converges. As it turns out, all the error terms that will come out are of order epsilon cube in this. So what you have is that because you know how to compute something for the model, because you know what f is, what you get is a martingale that is attached to the discrete model in a natural way. So now we have two tools. We have Loeffner's equation, and we have the fact that f is explicit. So now what I want to do is to compute something. I want to tell you what Zn, An, and Cn are. And then, well, I will tell you that because that's using the Loeffner's equation. And then what it will tell us is that this is almost equal to Z minus A over C minus A. And if you expand this, if you do a Taylor expansion around this point, then you will get equations that have to be satisfied by An and Cn. So what do you have? You have that Zn. So what is it? Zn is the image of Z by G at a small time. So it's well approximated by this. And what you get is that this is approximately Z, well, big Z, plus 2Tn divided by Z minus A. So this is just this at time 0. So you get something like this. Cn is the same. So Cn is approximately C plus 2Tn over C minus A. And this is given by Loeffner. And it's always plus big O of epsilon cubed. So this is a time derivative at 0, so of course it's not exact, but this is the leading term. Okay? And then, so what you do is you just replace inside the equation. So what do we have here? Okay. So what you get in the end is something like this. So let me call this function, what is it? Okay. What you do is you look at this for Zn, An, and Cn. You plug your estimates for An, Zn, or there is no estimate for An, but all I do is I write An as A plus the variation of A. So variation of A is just An minus A. And you plug this inside this, and you write that it has to be equal. So what you get is this. So I will first write the Taylor expansion without computing the derivatives. So what you get is, so there will be a second order term, which is like this. There's a second derivative in A of f times the square of the increment. But you know that, so the increment is like epsilon, but the rest will be like epsilon squared because the rest is of order Tn. So this is the only term of second order. And then there will be first order terms in all the variables. So there will be something like expectation of variation of A times dA of f. I'll put expectation in everything because that's what I'm computing here. And then there will be plus twice expectation of t. And this will come from this term here and here. So that will come in terms of d over dz and d over dc of the map. So there will be dc of f over c minus a. plus d over dz of f over z minus a. So this is the variation of this in time Tn. And we know that this is of order epsilon cubed. So this is what you get from having a martingale. This is true for every model. You don't need f to be explicit for that. Whenever you have some function that describes the limit, you have this equation. So far this is not specific to the uniform spanning tree case. But now what holds is that f is something explicit. F is written here. So you can compute the derivatives of f in z, in c, and in a. All you have to figure out is how r and theta depend on these. So that's kind of a heavy computation. But you can do it, and what you get is something like that. You get that, so some constant times the expectation of variation of a plus some other constant, in this direction, expectation of variation of a squared minus t. This is equal to 0. So this is what you get when you expand here. You have expectation of the variation of a squared. You have the expectation of the variation of a. You have the expectation of t. And all the rest is deterministic. So all the rest factors in. And you get these two factors here. And of course, this is wrong. There should be something like this here. There's an 8 here. So this comes from the computation. This 8 here is some feature of the observable. It's some sum of derivatives of this in different variables. So what you get is that this linear combination is equal to 0, and you get the value of 8 coming out of the computation. So somehow it tells you that 8 is hidden in the model, but it doesn't really explain why it's 8 and not something else. But 8 comes from the model. So we're not completely done yet, because we would like to have this equal to 0 and this equal to 0. And so far we have only one equation. So, well, going from this to two equations is not very difficult, actually, because all these are explicit as well. And these prefactors here depend on essentially c and z. So this depends on c and z. And this depends on c and z. So now what you can do is to write this equation for various values of c and z and hope that they are not all proportional to each other. But it's not a hope. You just write the equation and you notice that they are not always proportional. I'm not writing the exact coefficients, but they are explicit, so you can just do it. So you take two values of c, for instance, and you get two equations, like this equation star here. And they are linearly independent. So what you get as an output is like the expectation of variation of a is equal to 0, and the expectation of the square of variation of a minus 8 times t is equal to 0. So, of course, this is really a big O of epsilon cubed, and this as well. But morally, it's equal to 0. So that's what you end up with. You started from a model, you computed some observable, and then you encoded the discrete curve as the Loebner chain. And in the end of the computation, we get some information about the increments of the driving function for the discrete curve here. So this lives at scale delta, this lives at scale delta. And so the last step here is to say that an is the image of the tip here. So an is the same as the driving function. So if we know something about the increments of a, we know something about the increments of the driving function. This tells us that beta delta is centered. So it's like a martingale. It's centered. And this tells us that the variance of beta n, the variance of beta at time n, is approximately 8 times n. It's 8 times the time parameter of the driving function. So beta t. So this tells us that we expect the driving function to be close to Brownian motion at times 8 times t, which is the driving function of SLE8. So all we need now is just one last argument telling us that indeed this is enough to show that really you have something like Brownian motion. So the last step is something like score-hot embedding. So here I'm just doing a picture because those of you who know score-hot embedding, they will be bored, and those who don't, they will understand everything from the picture. So score-hot embedding will be some way to actually realize this random variable, the increment of a, as really an increment of Brownian motion itself. So this is a real valued Brownian motion. And the theorem tells you that if you have any centered variable in L2, so if x is in L2 and the expected value of x is equal to 0, then there is a stopping time tau for Brownian motion such that you can write x as a Brownian motion at time tau. So you can check that for plus and minus 1, for instance. If x is plus or minus 1, with probability 1/2, you just look at the first time the absolute value of Brownian motion is 1, and then you get plus or minus 1 with probability 1/2. So that's a trivial example, but from this you can build up by approximation, and you get this for any variable in L2. So here we have a variable in L2, which is the increment of a, because the increment of a is bounded by epsilon. So we can write the increment of a as Brownian motion at some time tau here. So this is tau, and this is a. This is the increment of a delta. So this is tau, and tau really depends on delta as well. Okay, so that's about the first increment of delta, of a. Now what you do is you start over here. So we have a new domain, which is the domain minus gamma up to time n, that you can continue and you can explore here, and what you will get is the same estimate for the increment of a between this step and the next step, but the formula will be the same. So you will get this at every scale, at every step of the exploration. And so what you get is, for the second increment, so really first you can map it to 0. So this will be an1, and this will be tau 1. This will be an2 at time tau 2, etc. And so what you have is the values of the successive values of a's here, and times at which you read them on the Brownian motion. And this tells you that the expectation of tau is the same as the expectation of a squared. So it tells you that there is a link between the variance of what you measure and the time in which you measure it. And it tells you that if you replace this Brownian by Brownian at scale at speed 8 times t, well, then you get a law of large numbers telling you that tau n behaves like n, the sum of squares of increments converges. And then all you have to do is then you let the mesh go to 0, and it will be a finer and finer approximation of this fixed Brownian curve. And this is enough to tell you that really the driving function as function of delta converges to Brownian motion as the mesh goes to 0. So I had no time to put all the details here. If you want, you can just figure it out for yourself. That epsilon cube is exactly what you need for that. That you will pile a few steps together and you will just accumulate the errors. But because 3 is large enough, the errors will still vanish in the limit. And what you get is that the driving function of the discrete curve actually converges to Brownian motion at times 80. Okay, so that concludes more or less what I wanted to say today. So this is more or less how you prove convergence of something to SLE. I realize it was a little bit more technical than the first 7 lectures, but somehow the aim was to study something about scaling limits. So I had to prove that, in fact, there were some things that actually converged to SLE. And this was the case of the UST. So as an exercise for next week, if you are bored, you can try to do the same for percolation. Now you have all the tools. You have Rousseau-Seymour-Welch to show that there is tightness. You have Cardy's formula as an observable. So that's a huge amount of work, but you can do it, and that's a good exercise. So, well, I guess I should stop here now. So thanks for your attention. Thanks for coming on a Saturday. And if there are questions, now is the time. No. No, he's still sleeping.